Hey there, welcome back to video 6-3, part 2. We are going to wrap up interpreting integrals in context. So let's go ahead and jump in. In this example, we have a graph here, v of t, and they say for 0 to 5 seconds, a particle moves along a horizontal axis with velocity, v of t, measured in meters per second. The graph of v is shown in the figure above. Interpret the following. Yes, position, velocity, acceleration is making a comeback, and we are going to go ahead and interpret these in context. And this is probably arguably the most applicable part of calculus is its applications and its tie-in into physics. So what I want to go ahead and do is I have three situations kind of laid out here, and we'll touch on them more in this semester. But I just kind of want to highlight similarities and differences in integration. So what I want you to notice that all of these have in common is that they are the integral from 0 to 5 of v of t dt. Now notice b has some absolute values, and I'll talk about that here in a second. And then c has a 1/5 out front. So let's go ahead and interpret. Again, think about the acronym CUT. So what we're going to go ahead and do here, right, is context. What is this? Well, the area under the curve of velocity, the accumulation of velocity is distance, right? Or in this case, from 0 to 5, it is displacement, right? I'm going right because it's above, and then I go back left. So this one is, we can say, the displacement of the particle from t equals 0 to t equals 5 seconds is 6.25, and I think the units here are going to be meters. Right? Yeah, meters per second. So notice something I have the context. This is displacement. Notice that I have units, right? T equals 0 and t equals 5 seconds, and then 6.25 meters, and I also have time. T equals 0 to t equals 5. B, how is B different? Well, I'm taking the absolute value of velocity, and really what this does to my curve, and I'll put this in red here, is it's going to take this portion of the curve, and instead of being negative, it is now positive, right? So the amount of distance I would go left, I am now going right. And so this is total distance. We have the total distance, and again, we'll cover this more in a lesson not too far away, aka the next lesson. The total distance a particle travels is 12.65, again, units, meters, time, from t equals 0 to t equals 5 seconds, again, the units. Okay, and so that's kind of just the difference. When you see absolute value of velocity, that's total distance. If you see the integral of velocity, that's displacement. And then I have this 1/5 out here. What the heck, 1/5? Well, if I take the integral of velocity, that is, again, that's going to be the displacement of this. But if I divide by 1/5, and really this 1/5 is, we're dividing, you'll notice that these fractions match the difference between your start and end point. That is going to be, you're dividing by your independent variable by time again. So really that's taking it back to velocity, right? So if I take this, the displacement is, let's say, 6.25 meters, but I divide by 5, then that's going to be the velocity, right? Your distance per time, okay? So meters per hour, right? 6.25 meters divided by 5 hours. So this is, and again, we'll cover this in another lesson, the average velocity of the particle. From t equals 0 to t equals 5 seconds is is 1.25. And the units here are meters per second. There you go. Okay. All right, wrapping this up, we have one more example here where we have a tabular form, and we have a table of values with gallons given, and then we have miles per gallon, which is a rate. On a recent road trip, Mr. Passwater decided to track his gas mileage during the trip. The efficiency of his car can be modeled by the differentiable function m of g, measured in miles per gallon, where g is the number of gallons of gas he used on the trip. Selected values of m of g are given in the table above, and it's known that m is decreasing for 2 to 12 gallons. A. Estimate the value of 2 to 12 m of g dg using a right Riemann sub with 3 subintervals as indicated by the table. Go ahead, try this now, see if you can get this. Pause me and we'll check out the answer. Okay, here you go. Here is the solution. 3 width times height, we're going to use 28 since it's a right Riemann sum. And then 5 times 26, 2 times 25 should give you 264 miles. Hopefully you got that. B is the estimate from part A an over or under approximation of the integral of 2 to 12 of m of g dg. Explain your reasoning. Since this is a right Riemann sum and it's decreasing, this is going to be an under approximation. Man, you know what? I never remember. I always just like to draw an arrow, and I like to use right endpoints. And yep, under approximation. So we can say under approximation because this is a right Riemann sum, and m of g is decreasing. So there you go. Not too bad. Okay, and then C, last part here. Using correct units, interpret the meaning of 1/10 of 2 times the integral of, 1/10 times the integral from 2 to 12 of m of g dg in the context of the problem. We could say 1/10 of the integral from 2 to 12 of m of g dg is the average. It's the average value of whatever m of g is, and that's his gas rate, right? Or gas efficiency, or oh my gosh, what is it called? Fuel efficiency? Should I just like not pause the video until I figure this out? What is it called? Your oh my gosh. Let me know in the comments. I'll use that. Let me know in the comments. What is it called? M of g dg is the average value of, oh my gosh, miles per gallon from t equals 2 to t equals 12. And our units here are gallons. Okay, let me see. Okay, so I had to look it up. Fuel economy. I guess up here it says the efficiency of his car can be modeled by a differentiable function m of g. Average value of fuel economy. I think that's a fuel economy. But yeah, it's your MPG, right? Miles MPG. That just sounds wrong because MPGT Academy. Oh my gosh. Hey, that's going to do it for this video. We interpreted more integrals in context in this. Drop a thumbs up. I'll catch you in the next video. See you later. Alligator, crocodile.